Welcome to this virtual field trip that is located in a very complex structural context. We are in the northern Apennines mountain range north of Italy. To understand the geological context, let's go back to the Pangea breaking, so about 200 millions of years ago. In fact, the northern Apennines derive from geological events that characterized the interactions between two tectonic plates, the European Iberian Plate and African Apulian Plate. These two plates were separated by the interposed Piedmont-Ligurian Ocean that was part of the larger Tatide formed after the Pangea breaking. After the Pangea breaking, the Piedmont-Ligurian Ocean underwent first rifting, then convergence, that initially led to the alpine east-dipping subduction of the European Plate below the Apulia African Plate, and then to the Apennine west-dipping subduction of the Apulia African Plate below the European Plate, and to the Alpine collision. To make a long story short, in the northern Apennines the final result is the superposition of two tectonic units, the Ligurian unit on top of the Umbrian-Tuscan unit. These two units are different in paleogeographic origin, lithology, and tectonic structures. The Umbrian-Tuscan tectonic unit, originally located more eastwards, is made of Apulia African continental shelf rocks on which rest, even if partially detached and deformed, the original sedimentary successions. The Ligurian tectonic unit, originally located more westwards, is made of several formations sedimented in the Piedmont-Ligurian Ocean. These formations have abandoned their original oceanic crust substrate, mainly disappeared in subduction, to overthrust from west to east, Apennine vergence, on the Umbrian-Tuscan tectonic unit as an allochthonous blanket. However, the area where we are going to focus the attention is close to the junction of two origins, the northern Apennines and the western Alps, the so-called Ligurian Alps. In fact, these two origins represent part of a continuous orogenic system derived from a complex space-time interaction between the two European and African plates and the interposed oceanic domains. Therefore, the geological features of the Alps-Apennines junction area show structures and sedimentation history associated with complex interfering processes developed during successive stages of growth of the different segments of the orogenic system. These stages of growth are related, according to the interpretation generally accepted by most geologists, with subduction which changed and reversed during time. Initially, the alpine east-dipping oceanic subduction of the European Plate below the African Plate, and then with the Apennine west-dipping subduction of the African Plate below the European Plate. Really, a very complex scenario. The relationships between Apennines and Alps, although highly debated by geologists for more than 1 century, are still incompletely solved problems. So these issues are, of course, outside this virtual field trip province. However, the observations that can be made in this area are very interesting to get an idea about the very high geological complexity that is usually underestimated and poorly perceived. In fact, the main targets of this virtual field trip are the understanding of the complex geological context and the observations of some outcrops with some considerations about the relevant rocks fracturing. So to start this virtual field trip, let's move from the nice town of Parma in the Padania Plain to go southwards inside the Apennine mountain range. We go up the Tero riverbed, a right tributary of the Po River, and we enter initially in a hilly countryside, passing then to the mountainous area of the Parma province. Just after the small town of Fornovo, we leave the Taro riverbed for its left tributary Ceno River that we are going to follow up to the small village of Varsi. The crossed countryside is a little wild and abandoned because sparsely populated, having experienced a strong and continuous migration of the population in the last 2 centuries. Initially, before the First World War, mainly towards very far destinations like France, England and the United States, and more recently after the Second World War, mainly towards the richer and more industrialized cities of the Closed-Po Valley. It is a region worldwide famous for its gastronomic excellences, such as, among the others, Parmesan cheese, raw ham, cured meats, tortelli, torta frita, etc. Here, from the small village of Varsi, we will try to give a look at the present geological setting, making a kind of cross-section that moves from the top of the Carametto mountain peak, standing out on the mountain crest, bordering northwards the Ceno Valley, to the top of the Dosso mountain pike, standing out on the mountain crest, bordering southwards the Ceno Valley, a geological cross-section passing through the very characteristic mountain pike of La Rocca. Before going into details, let's start saying that, based on the geological map, all the rocks crossed by this geological cross-section are related to several different geological formations that were formed and sedimented many years ago, in the geological time gap included between 95 and 45 millions of years. So in the Cretaceous, Paleocene and Eocene geological eras. The geological context in which these rocks formed was that of the Piedmont-Ligurian Ocean, the Paleo-Ocean separating at that time the European Iberian continent, located northwards, from the Apulia African continent, located southwards. According to the interpretation generally accepted by most geologists, the rocks outcropping along this Carametto Dosso cross-section belong to the so-called Ligurian units that were sedimented in this Paleo-Ocean. Following this interpretation, the Ligurian units are divided into 2 main groups in relation to their paleogeographic location: the internal Ligurian units and the external Ligurian units, being the first group considered to be placed northwestwards in the Ligurian Piedmont Oceanic domain, whereas the second group is located more southeastwards at the edge of the Apulia African continental margin. This subdivision is inferred by some specific features observed on the outcropping rocks. In fact, on one side, the internal Ligurian units include at the base Jurassic ophiolite sequences that are the remains of the oceanic crust. The ophiolites are still present at the base of a continuous sedimentary succession characterized by siliciclastic turbidites of late Cretaceous, early Paleocene in age. On the other side, the external Ligurian units are characterized by the absence of ophiolite sequences at the base of the sedimentary succession and by the widespread occurrence of the late Cretaceous carbonate helminthoid fleisch. Moreover, always according to paleogeographic considerations, the external Ligurian units have been further subdivided considering the lithostratigraphic features of their basal complexes. The first external Ligurian group, the inner successions, includes all the rock successions characterized at the base by the occurrence of sedimentary melange with both oceanic and continental blocks. The second group, the outer successions, displays rock successions showing a sedimentary base derived only from the thinned Apulia African continental margin. Let's now focus the attention on the tectonic phases affecting the Ligurian units. It is widely accepted that deformation of the Ligurian units is linked initially with a late Cretaceous Middle Eocene alpine east-dipping oceanic subduction of the European plate below the Apulia African plate. Initially, in the late Cretaceous, it is assumed the presence of a tectonically active double verging accretionary wedge that is a buildup of sediment scraped from an oceanic plate by the overriding plate during the process of subduction. This elevated accretionary wedge separated the internal Ligurian successions from the external Ligurian successions. It develops as compressional fold and thrust belts incorporating material of the Piedmont Ligurian oceanic domain, that means ophiolites and Ligurian unit sediments. As no sedimentary rock of age younger than the Middle Eocene is documented in the Ligurian units, Middle Eocene is usually regarded as the age of the closure of the Piedmont Ligurian Ocean. So with the Middle Eocene we have no more sedimentation and the end of the alpine east-dipping oceanic subduction. However, deformation did not stop at this stage because of the continuing convergence between the European plate and the Apulia African plate that caused the eastward propagation of deformations. Moreover, it triggered, in the late Eocene, the reverse of subduction transformed into the west-dipping Apennine subduction of the Apulia plate below the European Corsica-Sardinia microplate. This event produced the settlement of the Apennine orogenic accretionary wedge that incorporated the already deformed Ligurian units. So, the Apennine orogenic wedge includes deformed remains of the Alpine orogenic accretionary wedge. We can say that from the late Eocene, the general scenario is dominated by wedge-shaped stacks of thrusts spreading from west to east. In this context, the internal Ligurian units are interpreted to occupy a structural position on top of the external Ligurian unit's inner succession, and in turn, the inner succession on top of the outer succession. As a matter of fact, the very intense deformations affecting the external Ligurian domain, on which we are going to focus the attention, are the result of both the Alpine and the Apennine deformations. However, the most intense deformations and faulting appear to be sealed by the Epiligurian succession that was sedimented from the Middle Eocene to the late Miocene, so just after the end of the Alpine subduction. This Epiligurian succession is interpreted as sedimented within minor basins placed on top of the Ligurian thrust sheets at the top of the orogenic wedge. In fact, the Epiligurian succession lies on top of the Ligurian units through a regional angular unconformity Middle Eocene in age. This Epiligurian succession is not significantly deformed compared to the underlying Ligurian units, recording just the deformations related to the eastwards transport of the Apennine orogenic prism wedge. So, Despite being in the Apennine, the overthrusts and faults that we are going to observe in the geological cross-section between the Caramito and the Dosso mountain peaks appear to be related more to the Alpine rather than the Apennine origin. This aspect is clearly highlighted by the cross-section reported in the geological map passing eastwards of the Monte Dosso crest. In fact, the Epiligurian succession, just gently deformed, lies unconformably on top of the Ligurian succession, strongly deformed, being affected by bending, faulting, and thrusting. Based on the published studies, the internal and the external Ligurian units, inner and outer successions, include in turn, at a lower hierarchical level, different formations having different characteristics. The aerial distribution of these different Ligurian units results quite complex, as illustrated by the map. As you can see, the internal Ligurian units, in dark green, are located more southeastwards and overthrust on the external Ligurian units, the inner units in blue and the outer units in yellow. With this interpretative cross-section, this complex scenario can be tentatively illustrated. The internal Ligurian units overthrust on the external Ligurian units that in turn overthrust on the Tuscan units, which rest, even if partially detached and deformed, on the metamorphic Apuan Alps and on the Adria continental basement. This sequence is locally topped and sealed by the Epiligurian succession. The cross-section that we are going to analyze is located in an area dominated by the external Ligurian units, both inner and outer successions. Actually, we are going to cross different units as illustrated by the geological maps. Let's start going through the geological cross-section following the topographic profile and the geological map. The point of view from which we are going to analyze the cross-section is from west and south. So, trying to go in more detail, this is the altimetric profile of the cross-section passing through the Caramito La Rocca and Dosso mountain peaks, crossing the Ceno River Valley. The Dosso mountain flank is affected by the presence of two faulted zones. Starting from the Caramito peaks, we found, along the cross-section, the Monte Cassio flysch overthrusting on the older Scabiza sandstones. Both belong to the Cassio tectonic unit. Then, overthrusted by the Scabiza sandstones, we found the Complesso di Pietra Parcellara, that is a polygenic breccias belonging to the Grappallo-tectonic unit. Then, overthrusted by the Complesso di Pietra Parcellara, we found the Bettola flysch belonging to the Bettola tectonic unit. In turn, the Bettola flysch overthrusts the formations of the Farini tectonic units, on top of which we found the small clipper of oceanic crust represented by the ophiolite of La Rocca. It is a very complicated geological scenarios where different tectonic units, estimated sedimented in different areas of the Piedmont Ligurian Ocean, have been chaotically merged during the deformation history. To make this scenario even more complicated, is the geological setting of the different formations that are turned upside down. This aspect is clearly highlighted by the Farini tectonic units that result upside down, with the older units on top of the younger units. The same upside-down setting can be observed in the other formations. Moreover, at the top of the Carameto mountain peak, we can recognize the presence of a recumbent fold gently tilted northwards. So the complexity is highlighted by several features: the chaotic presence of different tectonic units, the widespread presence of overthrusts, the presence of an ophiolitic clipper, the widespread presence of reversed successions, and the recumbent fold. Let's spend some words for each item. Let's start from the presence of different tectonic units. Despite their different paleogeographic origin, we have a chaotic presence of both inner and outer successions units in the same area. They have overthrusted each other. Cassio is on top of Grappallo, that in turn is on top of Bettola, that in turn is on top of Farini tectonic unit. So, despite the geological cross-section includes just the external Ligurian units, we observe several different formations sedimented in different paleogeographic context, but then mixed up and overthrusted each other during the build-up of the alpine accretionary prism. The second issue is the presence of several overthrusts. We observe, in fact, the presence of 4 overthrusts plus an ophiolitic small clipper. The presence of these overthrusts is somewhat mirrored in the morphology of the southern flank of the Carameto mountain. They are probably mainly related to the build-up of the alpine accretionary prism. Another complexity is represented by the presence of the ophiolitic clippae, remains of the old oceanic crust on which the internal Ligurian units sedimented. In fact, La Rocca is a very characteristic mountain peak with its mottled dark green rock. The rock appears to be highly fractured, and this characteristic could have practical implications. In fact, for years this rock has been quarried in the northern Apennine and also in this area as inert material, poor material, with little economic interest. However, recently, to meet the goal of limit global warming, new technologies for carbon capture and storage have been tested, injecting directly CO2 into ultramafic formations like ophiolites for mineral carbonation. This approach is based on the reaction between CO2 and divalent cations, like magnesium, resulting in the bonding of CO2 into the structure of newly formed carbonate minerals. In this way, a mineral trapping is achieved, a process that is natural, also observed in the close Tuscany outcrops of Monte Castelli, Castiglioncello, and Malentrata. Therefore, this kind of rock could gain in the future a by far larger interest, and in this process, the fractures network would have a very important role in improving the effectiveness of mineral trapping. This issue, the widespread presence of reversed successions, is quite peculiar and is related, by geologists, to large recumbent folds. However, this explanation appears, in my opinion, questionable. we can sketch that a large recumbent fold is the result of rocks deformed by compressional forces, passing through different steps here, schematically illustrated. Initially, a symmetric fold, passing to an asymmetrical fold, then to an overfold, and finally to a recumbent fold. As you can see, the recumbent fold is characterized by a reverse segment where the stratigraphy is upside down. According to some interpretations, the widespread presence of reversed successions superimposed on each other would be related to this kind of events. However, this explanation appears questionable because these inverted series always lack a connection with the respective normal sides, and moreover, without any evidence of erosion that would have caused their disappearance. So this explanation appears quite weak, questionable. Probably these reverse successions could be related to the compressional deformations active for a very long time, during all the 2 phases of subduction exacerbating rock folding until their total overturning. Let's give a look at some interesting outcrops. To do this, we change our point of view from which observe the cross-section, before from south and now from north. We go to see an outcrop located along the Ceno riverbed. We are on the northern flank of the Dosso in an area affected by faults. As already said, the stratigraphic sequence of the Farini tectonic unit is here upside down. So the strata that we can observe along the riverbed lie with the older formations on top of the younger ones. The outcrop that we are going to observe is located in this context. Here we can observe a small antiform. Because of the multi-phases of deformation, the rock strata are highly fractured and deformed. The interpretation is that a first phase of deformation, D1, defined a very large recumbent fold, and so the upside-down stratigraphy. The entire Dosso mountain is made of this upside-down strata of the recumbent fold, while the respective normal sides of the recumbent fold disappeared, being eroded. Then, a second deformation phase, D2, became active, determining the formation of this small antiform. So, this small antiform is related to a second phase of deformation, acting on the reverse sequence, remains of a large recumbent fold. It is associated with transpressive faults characterized by both vertical and horizontal displacements. Just on the other side of the Ceno riverbed, a few hundred meters upstream, we can observe, at the foot of the Carametto mountain, another interesting outcrop. We are always in the Farini tectonic unit where the stratigraphy is upside down. So with the older layers on top of the younger ones. in a small lateral valley, we can observe the surface of a layer because its cover has been eroded. Actually, since the stratigraphy is upside down, what we observe is the bottom of the layer. Just to understand the context, we can say that after the layer's sedimentation, we had the overturning of the strata because of tectonic deformation, and then a partial erosion of an overturned layer. So it is put in view the bottom of the next layer. That is what we can observe in this outcrop. The surface is quite bumpy, locally characterized by elongated humps that are nicknamed as sole structures because they are found on the sole of the sandstone beds. Their mode of formation started from a pre-existing sedimentary shaly substrate which, in a context of strong current flows, got locally eroded, making small elongated holes or depressions. Then these holes got filled in with an overlaying deposit of sandy sediment. Then, along the geological times, the lithification processes transformed the soft sediments in hard rocks of claystones and sandstones. Once the strata were overturned and exposed to weathering and erosion, the claystone resulted to be much frailer than sandstone, more prone to be eroded. Therefore, the sole structures are preserved not as their original negative shape, the holes or depression, but as the positive shape that results when the holes are filled, so the cast of the holes. Based on the shape of the cast of the holes, the paleocurrent flow direction can be inferred. The last issue is the presence of a recumbent fold that can be glimpsed among bushes and shrubs on the southern flank of the Caramito mountain. Let's give a look. Actually, the outcrops of the Monte Cassio Fleisch recumbent fold are difficult to observe at the Caramito mountain, as they are largely covered by vegetation, trees and bushes. What we can glimpse is the gap in the vegetation defined by the absence of trees in correspondence of the thicker layers of sandstone, where vegetation has not been able to take root. These tracks draw the shape of the recumbent fold. In fact, not too far from here, we can observe the Monte Cassio Fleisch reference outcrops. As you can see, it is a very thick formation made up of cyclical alternations of sandstone, marly sandstones, marl and clay layers that draw on this outcrop a broad syncline. Therefore, only thanks to the cyclic presence of this thick layers of hard rock that we can observe the recumbent fold of Monte Caramito. This fold is the result of the deformation history affecting the external Ligurian units. According to the geological map, the The different components were recognized that are the syncline and the anticline of the fold. And this is the end of this virtual field trip. If someone would be interested in investigating more in depth the subject, here you can find a short list of papers to refer to. So long.